everyone, I'm Sandy Lucas, the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us for the first session of the webinar series called Tropical Pacific Observing System Process Studies. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. If you've missed any of our prior CVP webinar series, I encourage you to view them from the website. Today's session will also be posted there soon. I'm excited to launch this series today. CVP supports research that enhances our process-level understanding of the climate system through observation, modeling, analysis, and field studies. The topic of this series is the tropical Pacific Ocean, and its focus is to build upon and refine scientific understanding of the tropical Pacific climate system. The tropical Pacific region is important to climate variability due to its role in the El Niño Southern Oscillation and the teleconnections to the United States weather and climate. Outcomes from these projects will be used to further the development of possible field campaigns in this region. This webinar series covers the 8 projects funded by CVP, which started in September of 2018. The goal of these modeling studies is to refine the current scientific understanding of the equatorial Pacific climate system, with a specific focus on 2 process studies identified in the TPOS 2020 first report. The first is the Pacific Upwelling and Mixing Physics, or PUMP, and the second is air-sea interaction at the eastern edge of the warm pool. As I mentioned earlier, these results will assist in the planning of future field campaigns. I look forward to hearing the results of these projects in the webinar series. I would like to thank Jose Algren, the CVP program specialist and the organizer of this series, for all the hard work that he has done putting this together. At this point, I'll turn it over to Jose for the full introduction of the series and our speakers today. Thanks, Jose. Anytime you're ready.
All right, thank you so much, Sandy. Hi, everyone, and welcome to the first of 5 webinars on the topic of the Tropical Pacific Observing System TPOS process studies. Each of the sessions will feature 2 presentations and will run from today, September 22nd, 2022, to November 10th, 2022. The series of presentations will share the latest results of these projects and will allow the researchers to discuss the importance of their work, outcomes, and lessons learned with a broader scientific community. We hope you will enjoy today's talk and ask questions. Speaking of questions, if you have any and you would like to ask the presenters, please use the raise your hand feature, which you can find on the control panel for the GoToWebinar on your right. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using their audio. You will need to unmute yourself too after I do so over here. If you have audio problems, I will ask you to type your question into the questions box. Can you also find it on the GoToWebinar menu on your control panel? Now, without further ado, we're going to present our first speaker of today. She is Dr. Anna Deppenmeyer from the National Center for Atmospheric Research, NCAR. Her research focuses on the interaction between the ocean and the atmosphere and the effect of the small-scale processes such as mixing on large-scale properties and vice versa. Dr. Deppenmeyer, thank you so much for joining us today. At this time, we'll turn the controls over to you.
Thank you, Jose, and thanks, Sandy, for setting this up. Yes, I can share my screen. Okay, I believe you can now see my screen. Yeah, thanks, Jose, for the introduction, and I'm really excited to be kicking off this series of webinars. I'm going to be talking about our results that we found out together with Frank Bryan, Billy Kessler, and Nguyen Thompson at this first stage of the Tropical Pacific Observing System pre-field modeling studies. And I'm going to be talking about diabatic upwelling in the Eastern Equatorial Pacific. Before we jump into the results, I wanted to remind everyone what I mean when I talk about diabatic upwelling. So if we look at the Tropical Pacific, sort of roughly sketched out here with the upward sloping thermocline towards the east and a deeper thermocline in the west, We're looking along the equator here at a cross section, and so this would be the equatorial undercurrent that flows from west to east along this upward sloping thermocline. And just if a water parcel follows the path of the equatorial undercurrent, starting here, for example, and then flowing up this path to the east, it actually performs movements in two directions. So it moves eastwards, obviously, but it also moves upwards. And this is what we call adiabatic upwelling. So the water parcel that could be, for example, 20 degrees Celsius, that's set here, moved along with the EUC, but also along with the upward sloping thermocline. It didn't take up any heat, it didn't change its temperature, so this is an adiabatic movement. What I want to focus on today is the diabatic component of the upwelling. And this is what we usually think about if, in these diagrams of the tropical Pacific circulation, we see the equatorial undercurrent moving east and upwards and the surface currents westward, and then we draw this upward arrow sort of across the thermocline like I've drawn here. This is actually a diabatic upwelling, because for this parcel that sits here at maybe 19 degrees Celsius to cross the thermoclines and become warmer, it needs to take up some heat into the ocean. And this is the component that we want to talk about and that we focus on our work. There's two ways that you can diagnose this diabatic upwelling that, again, is connected to heat uptake into the ocean. And one is the kinematic perspective, where you look at these upward sloping isotherms here, for example, the 20 and 21 degree isotherm, and then you define a box on the edges of those isotherms, for example, east and western box. And then you would diagnose the diabatic upwelling as the difference between the movement across the upper isotherm that bounds this layer minus the movement across this lower isotherm that bounds this layer. And I've already said a couple of times that I'm concerned with movement across isotherms. So the CI here still stands for cross isothermal motion. And the way you can calculate this is by taking the difference between the divergence in this isothermal layer and the movement of the isotherm itself. And this is how you could get to diabatic upwelling from a kinematic perspective. And there's another perspective that is connected to thermodynamics. That is the one that I'm focusing on here. And you can understand that as the movement of the parcel in the direction of the temperature gradient, so the Grangian movement of the parcel across isotherms, so in the direction of the temperature gradient, plus the movement of the isotherm itself. And this we can connect to the heat budget, which really conveniently lets us identify the processes that drive this diabatic upwelling. Some of these processes I'm going to highlight, and that's the solar penetration, a vertical mixing component. Here we have a component arising from horizontal mixing. I didn't give it a signal or symbol, spoiler alert, because it's very small. And then we have some covariance term that arises from the averaging operator that we apply. I'm happy to talk about that in detail more. It's also described in the papers, but you could consider this an eddy stirring term. And then we have higher order terms that sort of falls off the page here. Unfortunately, those are very small. We can't compute them, but they are very small, so we can happily neglect them. There's one important difference between the thermodynamic and the kinematic estimate, and that is that the kinematic estimate is always strictly vertical, but the thermodynamic estimate of diabatic upwelling is directed into the temperature gradient, so it's normal to the isotherms. So that is a good approximation for vertical movement when we're in the thermocline, where the gradient is mostly vertical, but when we're in the mixed layer, we have horizontal gradients that will be bigger than the vertical ones, and then this thermodynamic estimate gives you a temperature or a heat transfer, but not an upwelling in the sense that we usually think of it. I've done all my analysis on 36 years of a 1/10 of a degree pop forced ocean simulation, for which we have a heat budget available. And these simulations are validated in the papers that I'm citing throughout this presentation, so I'm not going to be talking about the validation now. So we start by looking at diabetic upwelling in the long-term mean, and I'm just showing you a small part here of the tropical Pacific. So we have the coast of South America here, and then we go all the way over across the date line. So a fairly large region longitudinally, but latitudinally, we're only looking at -3 to 3 north. So what you can see here is this diabatic upwelling, so vertical motion that takes up heat and transforms the temperature of parcels across the 22 degrees Celsius isotherm. One thing that I will be doing throughout this talk is look at these diabatic upwellings in temperature space rather than depth space, because that way we can get a clearer signal of how the parcels are transferred from one temperature to another without seeing too much of the movement of the isotherms. Okay, so you can see that this form or this shape is very much reminiscent of the coltan. It's a very narrow region though, and really only spans ±1.5 degrees around the equator. And we have a strong signal in the east, and then it becomes weaker as we move towards the west. Another thing that's interesting here is that we have a positive maximum north of the equator up to 125 west, and then we have a positive maximum south of the equator further east of that. And we can see that also if we look at cross sections across the equator. So I'm showing you these lines here, cross sections along the lines that I've drawn at 155, 125, and 110 west. And again, we're looking at temperature space here. This hatching denotes isotherms that are present less than 50% of the time. So that means that the closer we are to the hatching, the closer we are to the actual surface. And you can see this V-shaped signal here across all longitudes. And as I've already mentioned before, you can really see this shift of maximum WCI or diabatic upwelling south of the equator, whereas further west, it's north of the equator. And one interesting thing is that we have a lot of signal here close off the equator, close to the hatching, which means that we are in the thermocline here. We are not in the thermocline, we are in the mixed layer. Yeah, I wasn't sure which arrow will come up first. So this diabatic upwelling signal here close to the hatching would be in the mixed layer, and it would be more of an off-equatorial movement rather than a vertical, while if we are looking at the signal in the thermocline down here in these colder temperatures around 20 degrees Celsius, we're really talking about the well vertically stratified region where this diabatic upwelling is a typical upward movement. So that's what the diabatic upwelling looks like, and the great thing that we've been able to do with our thermodynamics approach is that we've been able to drill down into the processes that drive this upwelling. And before we look at further results, I'm just going to show you a sketch of how it all works together. And so the main drivers of diabatic upwelling is solar penetration and turbulent heat. And so you can see here on this, again, cross-equatorial cross-section, where we have the equatorial undercurrent here that introduces shear above it, that introduces mixing, and therefore a turbulent heat flux. And then above it, we have solar penetration, so another turbulent heat flux. For water mass transformation, what we're really interested in is not the heat flux itself, but the heat flux divergence, because that's what will deposit or take out heat out of a layer or a parcel. And if we sum up the heat flux divergence of solar penetration and vertical mixing, we get this symbol or this signal, which corresponds to what we actually see in our analysis. So this is at the equator at 140 west, the signal cross isothermal velocity or diabatic upwelling, which consists of vertical mixing and solar penetration. We can see that it peaks a little bit above the core of the undercurrent, again consistent with where there's a lot of shear. And another thing that I just wanted to point out is that I've also drawn here the total Eulerian velocity, so the total upwelling, and this is the diabatic component of that. So you can see that the rest of that would be the adiabatic component. But this diabatic component does make up to 1/3 of the total velocity. So this was the schematic. Now here's the data from our model simulation. In fact, this V-shaped signal that we've looked at before. Just now it's at 140 west. This is the vertical mixing contribution to the diabatic upwelling and the solar penetration contribution to diabatic upwelling. If you add these two together, we get this signal, which is very close to the total. So we can safely say that in the long-term mean, in fact, vertical mixing and solar penetration really dominate the diabatic upwelling. The same holds if we look at variability on timescales such as ENSO. So we first split our simulation in El Nino, neutral, and La Nina phases, and then diagnosed diabatic upwelling again. You can see that during El Nino, there's much reduced diabatic upwelling, and during La Nina, it's stronger than usual. And again, these signals are really composed out of the vertical mixing components and the solar penetration components. So those are our results from, or some of the results from interannual and long-term timescales. I'm thinking about a field study, and specifically maybe also a shorter term field study. We wanted to look at shorter timescales and the variability thereof. So we're now going to be looking at diabetic upwelling in the seasonal cycle, and this is a study that's just recently been accepted in JPO. So you see that there's some variability here indeed. So in January and winter, we have some strong diabetic upwelling, which really seems to shut down in boreal spring, and then comes back up in summer and persists throughout fall. And now we wanted to have a closer look, so we're going to be looking at the 3 locations that I've marked here with the star. And these are, for those 3 locations, in temperature space, the seasonal cycle for diabetic upwelling. And this is the total signal in colors. So you can see that diabetic upwelling, so before what I showed you was an average between 24 and 20 degrees. So we see that we captured nicely this region, but instead of just seeing a weakening or a strengthening, we now see also a movement of our diabetic upwelling signal along with the seasonal cycle. And an additional information that I've added here is the stippling indicating solar penetration driven diabetic upwelling when solar penetration contributes more than 0.3 meters a day, and the same for vertical mixing in the dashed lines here. So this lets us see, if we just focus on one location for now, for example, the 0 north, 125 west, you can see that there are 2 maxima actually. So there's one maxima here in spring that we didn't pick up in the map before, and then there's one maxima later in the year during July. And most of the colored signal follows the vertical mixing driven component of diabetic upwelling. But then, in fact, in spring, this maximum in spring really coincides with solar penetration driven regime, where this vertical mixing doesn't contribute quite as much as it would here, where it's the sole driver. And so looking at the vertical shear, on the seasonal cycle of vertical shear at those locations, also in temperature space, helps us see this more clearly too, because the vertical mixing component is going to be driven by the vertical shear. And so here we can clearly see that at all locations there's a maximum in vertical shear in summer coinciding with these WCI maxima, but in spring there are no such maxima, and in fact we can really see that there's a minimum, so the solar penetration component here is strong enough to overcome the vertical mixing component. And so we can conclude that there are 2 regimes in diabetic upwelling throughout the year, and then one is the vertical mixing sort of traditionally long-term regime where vertical mixing through vertical shear really drives the diabetic upwelling, but then in spring we have these maxima that coincide with the solar penetration. And one other thing to point out again, or one related thing to point out, is that when we have these maxima in spring, that's also when we have warm sea surface temperatures. And these maxima move up in the water column. So they're much closer to the surface and much closer to the mixed layer than the maxima that are driven by vertical mixing. So therefore, these solar penetration maxima can really be viewed as off-equatorial heat transport rather than diabetic upwelling in the sense of a upward movement of the water parcel. We've then looked at even shorter timescales, so subseasonal, and when I say subseasonal, we've been focusing on tropical instability waves. which have a period of 3 weeks to 4 weeks. And I'm indicating the presence of tropical instability waves in these Hofmüller diagrams here with these black dots. So whenever the black dots move further right, we have high tropical instability wave kinetic energy, so the presence of a tropical instability wave. You can also see this here in the sea surface temperature Hofmüller diagram with these cold temperatures moving westwards in time. And you can recognize that if you look at the WCI field in the thermocline, this is the 20 degrees Celsius isotherm, you can see that you recognize some of these streaks also. And this is on the equator, so we're looking on the equator. And you can see that most of this signal here, which could also be viewed as a seasonal modulation, right? Because we know that there's less diabatic upwelling at these temperatures in spring than in the rest of the year. And most of this strong signal is driven by vertical mixing, as we've seen before, and we can also recognize these streaks in the vertical mixing. And now we also have a part of this eddy covariance, which is related to the eddy stirring that's introduced by the passage of a tropical instability wave. And we can see a little bit of heightening here later in the year, but we don't really see these streaks. If we now move off the equator, though, where we are away from the strongest place of the equatorial undercurrent, so away from this very strongly vertically shear mixing driven regime, we can identify again the tropical instability waves in the sea surface temperature and from the kinetic energy. We can then recognize the streaks here in the WCI field, and now most of the signal seems to be driven by this covariance or eddy stirring term. And there's some of it in the vertical mixing. I will just say that the fact that this shows up in the covariance term is because we're looking at 5-day averaged output. And I'm happy to talk about that more in detail, but this is indication that the tropical instability waves contribute to diabatic upwelling, specifically off the equator. So with those analyses, we can now look at a comparison across timescales. So I'm drawing here indication of the in temperature space as the seasonal cycle, the El Nino phases, and the tropical instability wave, high or low tropical instability wave, kinetic energy phases. And I don't want to get into detail too much on this part, but I do want to point out that the x-axes here are the same. So the thing to take away from this is that each timescale variability, tropical instability waves, and so or the seasonal cycle have similar amplitudes of diabatic upwelling, and they also modulate diabatic upwelling with the same order of magnitude. So all of these components are important, and observing them, or even one of them, will contribute to our understanding of this in the real world. So for the future work that we're really excited to be starting now, we will continue to investigate the temporal and spatial scales of WCI variability. And we're talking here about vertical and horizontal scales with the aim of identifying a field campaign and locations that could best prepare us for observing the quantities that we need to diagnose WCI. So here I'm just showing you a snapshot of a tropical instability wave that you can clearly identify, but the field that I'm showing is WCI. So you can clearly see this modulation of diabatic upwelling by the tropical instability wave. And we'll be looking at temporal and spatial scales at coherence and how these signals can best be detected in a field campaign. We'll also be looking at large-scale drivers of WCI and impacts on the large scale. And this is, for example, thinking about whether we can use some of the backbone measurements to parameterize or get to WCI in the absence of more specific measurements such as turbulence, vertically resolved turbulence. But really, the overall goal is to identify an observing strategy for a shorter-term campaign and from the long-term backbone array, and how we can best make use of it to get to WCI in the real world. And we'll be doing that from those two perspectives that I started out with, the kinematic and the thermodynamics perspective. This is the one we focused on so far, and now we'll involve the kinematics a little more and try to reconcile them in order to get at WCI from different time and spatial scales. And you can see here that WCI, if we average over a big enough box and a long enough time scale, We have the kinematic here in blue and the thermodynamic estimate in orange. They fit really well together as long as we stay in the thermocline. Here in the mixed layer, they deviate because they have different definitions. Same for averaging over different temporal and spatial scales. We're hoping to come up with a strategy so that we can long-term monitor WCI. And that's it from me. Thank you very much.
Thank you so much, Dr. Deppenmeyer, for that excellent presentation. We're going to open up the floor now for questions, if anybody has one for Dr. Deppenmeyer at the moment. Okay, since nobody has questions so far, we're going to move on to our next presenter.
Thank you.
She is Dr. Ariane Verdi from the Scripps Institution of Oceanography. Dr. Verdi is a programmer specializing in regional ocean state estimation. She earned a PhD in physical oceanography from the MIT Woods Hole Joint Program after studying engineering in her hometown of Montreal. Her current research projects span the Southern Ocean, California Current System, Red Sea, and of course, the tropical Pacific. Dr. Verdi, thank you so much for joining us. At this time, we'll turn over the controls to you.
Thank you very much. Thank you, Anna, for your great presentation, and thank you, Jose and Sandy, for having me and giving me the opportunity to present some of our work on the development of a high-resolution state estimate to study things like mixing in the equatorial Pacific Ocean. So this project started with the word key challenge, which is the task of quantifying the balances of mass, heat, and salt in the equatorial Pacific. And so Bruce Cornell and I were funded by CVP to quantify these budgets in a coarse resolution state estimate. And we've been collaborating with Anish and Matt's CVP funded project as well on this task. And then it has evolved into trying to understand the vertical balances and the connections between the surface and the thermocline. And so we have set out to make a small scale state estimate in the Central Eastern Pacific and assimilate observations from the Equator Mix field campaign. So these are the data here from Equator Mix. I'm just showing a preview here. I will come back to this figure later, but first I'm gonna start by explaining what is a state estimate. So our product is the Tropical Pacific Ocean State Estimate, or TPOS. And a state estimate is basically a synthesis of observations and models. In our case, the model is the MIT GCM in a regional domain that goes from 26 south to 30 north. The observations come mainly from satellites and Argo profiling floats and moorings. And we use the 4D VAR data assimilation methodology to constrain the numerical model to fit the observations. Our original product went from 2010 to 2019, and it has a relatively coarse resolution of 1/3 of a degree in the horizontal and 51 vertical levels that go from a 5-meter thickness near the surface and then increase thickness with depth. And our goals were to capture the large-scale patterns of the ocean state, as well as some mesoscale features like these tropical instability waves that we can see on this SST snapshot, as well as to quantify the volume, temperature, and salinity budgets and understand their interannual variability. So in particular, we're interested in the 2015-2016 El Nino event and how that changes, or how the changes in the winds affect the ocean properties in the equatorial strip. And we're focusing on the region here in the white box that goes from 5 south to 5 north. This is a busy slide, but there's just a few things that I want to highlight from it. The first is that on this time series on the left here, we have the model equivalent of the Nino 3.4 index in blue, and it is nearly identical to the actual Nino 3.4 index in black. So that gives us confidence that our state estimate is an appropriate tool for looking at ENSO-related variability. The next thing is that during the El Nino event, there are large basin-wide effects in, or changes in temperature and salinity. So in the middle column here, what I'm showing is time series of the depth of the sigma 25 isopignal, and then the top 300 meter average temperature and salinity. So this is average, again, in this white box, 5 south to 5 north. The state estimate is in black, and the blue curve is the Argo mapped product, which is interpolated from observations. And so many people are familiar with this, but during the onset of El Nino, we had a slight warming followed by a very large and rapid cooling, and then a substantial freshening of the upper ocean and a slower recovery. So this is for the basin averaged ocean state. We can also look at specific locations. And so here on the right, I have time series of 100 meter temperatures at 5 mooring locations along the equator. They are the moorings with the black circles around them on the map. So this is moving from the west part of the basin toward the east part of the basin. Again, the state estimate output is in black, and the blue is the actual observations from the town mooring. And I'm showing here that the response changes as we're moving from west to east. And I also want to point out that the town mooring data was not used in the data assimilation. So these are independent observations that we can use to validate our product, our state estimate. And we find that for timescales longer than 20 days, we have a good fit between the model and the observations. So before we get into the variability, it's a good place to start to look at the mean. And so I'm showing here some schematics of the mean volume and temperature budgets. This is for the period 2014 to 2018. And these little boxes are meant to represent the top 300 meters of the ocean from 140 east all the way to the east side of the basin, and from 5 south to 5 north. And I'm quantifying here the fluxes or the contributions from surface fluxes. Those are the blue arrows. And then we have zonal flow coming in from 140 west. We have the meridional flow at 5 south and 5 north, and we have the upwelling at 300 meters. And the horizontal flow can be decomposed into a geostrophic component and the ageostrophic component, which includes the Ekman transport. So without going into too much details, I just want to point out a few things. So these arrows here show the mean vertical and meridional circulation averaged over the basin. Same thing with, here's the mean temperature. And so we have input of mass and mostly heat at the surface. We have a zonal current coming in and carrying cold water, which takes heat away from the domain. We have Ekman flow going out of the equatorial region, which carries heat away with it. And we have geostrophic currents in the opposite direction. And then we have the upwelling, which brings in cool waters to the domain. We did this analysis and closed the budget for salinity as well, although I'm not showing it here for the sake of time. But I would say that we have solved the word key challenge, at least for the period, the 5-year period that we've analyzed with the output from our state estimate. And then we have also diagnosed how each of these arrows, how each of these fluxes changes during the onset and the recovery from El Nino. And that is all described in a paper that should be submitted any day, very soon, hopefully. Okay, here's a different way to look at the word key challenge. So this is the heat budget or the temperature budget, with each terms plotted as a function of depth. And this is for a single location in the pump region, so on the equator at 140 west. This is again from the state estimate. The first panel is showing the mean from a 4-month period in 2012. And the main contributions are from the advection divergence in red and the diffusive flux divergence in yellow. The next panel is showing the same terms, but vertically integrated from the bottom of the water column. So this yellow curve here is our estimate of diffusive fluxes. And I'm showing next to it a figure from a paper by Smith et al., where they estimated turbulent diffusive fluxes based on observations. And their curve, which actually is on a different scale, this is only showing the top 120 meters, but the shape of the curve and even the magnitude is actually pretty similar to our estimate here. So we found that encouraging, and it made us want to look more into mixing, upper ocean mixing. But with a 1/3 degree resolution, and especially our kind of coarse vertical resolution, that's not enough to capture the processes that are involved in mixing. And so that motivated us to start increasing the resolution of our state estimate. Another motivation to going to higher resolution is the development of new or the availability of new observations of the tropical Pacific Ocean. And one example is the biogeochemical Argo floats. So as part of the GO-BGC program, there are a few floats that have been deployed very recently in the tropical Pacific, and this is just one of them, deployed around 140 west at the end of 2021. And each black dot here is a profile of temperature and other properties measured by the floats, and the background color is the observed SST, and so the float is measuring the ocean while the tropical instability waves are passing through. And so Kaylee Jones is a graduate student who started looking at these observations. So the BGC Argo floats measure temperature and salinity like all other Argo, but they also have sensors for oxygen and nitrate, pH, chlorophyll, and backscatter. And so just one thing to point out is there's a fair amount of temporal variability, but there's also some interesting vertical structure, like we have these pH minima that arise once in a while in the thermocline. So there's lots to understand there, and interesting observations that we'll be looking into. So this is how we have set out to go from coarse to higher resolution. I'm currently working with the 1/6 of a degree setup, which has 66 vertical levels, and those have 2-meter thickness in the upper 10 meter of the ocean. And I'm also playing with a 1/12 of a degree setup, but the goal is to go to even higher resolution with a lot more vertical levels. But even at 1/6 of a degree, we see some significant improvements in how well we fit some of the observations. So for example, here I'm showing mean zonal velocity versus latitude at 2 locations along the equator. And the 1/6 of a degree model, which is the yellow-orange curve here, fits the black curve, which is the observations, better than the coarser resolution 1/3 of a degree model. This is 200-meter velocity. And these zonal currents, like the EUC and the jets, are very important in transporting tracers such as oxygen. So these plots here are from a simulation where we coupled our state estimate with a biogeochemical model that includes tracers like oxygen. So this is 100-meter distribution with the oxygen minimum zones, and then at 200 meters we see a big signature from tropical instability waves. So definitely important for tracer distributions. And then from the work of Deepak and others, we know that tropical instability waves are associated with deep mixing, and we looked a little bit into that in our state estimate. So here I'm plotting from the state estimate the Richardson number, which is a measure of shear instability. And we see that it is modulated by the diurnal cycle. So we have 1-day periods, and then at the base of the mixed layer, we have these red spots, which are unstable regions. So the question is, this is state estimate inferred Richardson number. Is that consistent with observations? So we saw an opportunity there in a data set from the Equator Mix field campaign. So Equator Mix was a cruise in October 2012 at 140 West on the equator, where they took a lot of measurements at very high vertical resolution. Their instruments included fast profiling CTDs and current profilers. So they have lots of highly resolved data at the same time as a tropical instability wave was passing through. And so what we are doing is a high resolution state estimate. So we're thinking 1/24 of a degree with about 225 vertical levels. That is going to be just a sub-region of the tropical Pacific, this black box here, and it's centered around the location of the Equator Mix field campaign and observations. And we're going to use the coarser resolution state estimate for the lateral boundary conditions. This is an example of data that we have from Equator Mix. So we have about a month of data in the upper ocean. So this is depth for top 300 meters. Here's the buoyancy frequency. And below that, we have the shear squared. And the bottom panel is the Richardson number. And I mentioned a tropical instability was passing through. So this happens here around the middle of the panels and causes some surface instabilities. And then the striking feature in these plots is all the very fine vertical structure that we can see throughout this month-long observation campaign. And so we we're going to assimilate these observations in our high resolution state estimate and are going to try to address these questions. So the first one is, can we fit the observations with our existing model? In places where we don't fit, it will point us toward model errors, and maybe the mixing parameterizations will need to be refined. We're going to diagnose the turbulent vertical transport of momentum, heat, and salt, and we're going to compare that with estimates from observations and from models. And we can also use the state estimate to determine which observations are most valuable to constrain whatever process we're interested in. So hopefully that can be helpful to address some questions of the pump field experiment. And so I will leave it at that. Happy to take any questions now if you have any, or feel free to contact me by email or otherwise if you are interested in chatting in the future. Thank you.
Thank you so much, Dr. Birdie, for that excellent presentation. Again, we're going to open up the floor for any questions for Dr. Birdie. All right, I see that Frank Bryan has a question. I'm going to unmute you, and please unmute you on your side too. Go ahead, Frank.
Can you hear me?
Yes.
Okay. Hi, Ariane.
Hi.
Maybe I missed this, but in your existing state estimates, or these ones you propose for the smaller domain, are any of the subgrid scale closure parameters actual control variables, or is this something you're sort of anticipating doing in a little more ad hoc way where you see what it is and then adjust manually?
That is a very good question. There's a Blue Angel plane that just flew over our house, so that was very noisy for a second. Sorry about that. So the high resolution state estimate, that's a subdomain, we haven't started using it yet. It's still in concept form. What we're going to start by doing is just having the observations as constraints and see if we can get anywhere near what the observations look like. So we're first going to try to diagnose where we do well, where we don't. Where we don't do well, we might think into either looking in different parameterizations or changing some parameters of, let's say the KPP or diffusivities. And we can certainly have at least some of those as control parameters that we can optimize with the adjoint. We can definitely optimize things like vertical diffusivity. But yeah, it's future work that we're super excited about, not something that we have tackled yet.
Great, thank you.
Thank you.
Again, we're opening up the floor for any questions that you may have for Dr. Birdie and or Dr. Deppermeyer as well, if you thought one for Dr. Deppermeyer as well. All right, I see that Sue Santo has a question. I'm going to unmute you, and please go ahead with your question.
Hello, sorry. Hello, can you hear me?
Yes.
Okay. Yes. Thank you, Ariane. I would like to ask a couple of slides before the end. You mentioned about the diurnal cycle. Does the modeling include the tide, or just showing because of the pattern?
We don't have tides currently, and that is something that we will add when we really set up this smaller domain with higher resolution. I have a domain in the California current where I'm setting up high resolution and including tides. So we haven't done it yet. Forthcoming.
Okay, thank you.
Okay, so we would like to thank our presenters, first of all, for joining us today. And all of you who joined as well for this set of presentations in our series on the Tropical Pacific Observing System process studies. We would like to thank today's presenters as well for taking time to share their work. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/cvp/webinars. We will hope you will join us for the next webinar on Thursday, October 6th, same time, same web link, as you can see on your screen. We're going to have Dong Xiaoxian from the University of Washington, Saildrung USV Pilot Studies for the Tropical Pacific Observing System, and Yanshu Xu from NOAA CPC and OSSE study on roles of Tau and Triton and Argo in Tropical Pacific Observing System. Sandy, if you want to say some last words.
Trying to find the mute button here. So thank you everyone for joining us for today's webinars, and I look forward to seeing the next set on October 6th. Thank you again for presenting today.